So let's explore a little bit about benchmarking, which is going to be useful and required for your first progress report. And overall, as part of any really good aircraft design, the first thing you want to do is go through a series of benchmarking analyses. Now, this all goes back to this idea of a new product, and specifically when we have a new aircraft design, we always have to say, well, why are we doing this? Why are we building a new aircraft rather than using the aircraft that are currently available on the market? Now, this requires us to look at two things. One is the basic physics, and when we have a new design, we have different elements on the cutting edge of various systems on board the aircraft that we're going to start looking at. So these will be structures, components, your propulsion systems, your avionics, your aerodynamics. So what is the art of the possible? So that's one extreme side. On the other side is, well, what can we afford to do? And this is driven by the various types of aircraft that we may look at. If we have a single aircraft that's going to be performing a very critical mission, obviously our cost is going to be very different from something that we're going to be looking at putting in the commercial marketplace. We combine these two things together, what do we get? Well, we get the engineering. So we have to have information on both of these things to really drive the overall design. Now, what benchmarking does is it helps us look at what's been done in the past. So we don't even really have to think about the overall physics. So we can look at different design parameters, such as wing loading, thrust to weight ratio, weight to power ratio, takeoff weight, range, endurance, number of passengers, all of these things, and see how they've evolved over time. And compare them with different designs. So benchmarking in part is, trying to intuitively think about some of these design drivers and look at some of our performance parameters. So an example is the sweep of Douglas aircraft. Now we start off obviously with the DC-3, then we go to the DC-4, 6, 7, 8, 9, and 10. Now what you'll notice is our propeller-driven aircraft with a DC-3 through 7 all had moderate sweep and relatively low Mach numbers. So ranging from 0.35 up to about 0.53. So we can see directly from this that there's some kind of relationship. And as we go to the jet-powered aircraft, which are much faster, traveling in the range of Mach 0.8, we have much more significant sweep. So immediately, without knowing anything about the physics, we can say, oh, there must be some relationship here. Now you have to be careful with any type of benchmarking. You can look at this and say, well, maybe the DC-3 was swept for some reason related to Mach number, but it actually had nothing to do with that. It was just a matter of matching the aerodynamic center with the center of gravity. Another example of this is looking at a vertical takeoff and landing versus conventional takeoff and landing. Compare that with your power ratio. So when you look at, say, an endurance factor in this case, power, weight, velocity versus the speed, you can immediately see, oh, fixed-wing aircraft are much more efficient, much faster than vertical takeoff and landing aircraft. So there is this relationship on this particular design. There's an upper limit, basically, on what you can do in terms of the overall velocity. Now, a good example to look at is Boeing. And so we have a large commercial aircraft manufacturer, and they're looking at their future product lines. And so the first thing that they would do is say, well, what are all the aircraft that we currently have in our catalog? What customers have an option of choosing from? And then start comparing across an overall range of different options. And this is one of the things that they were looking at, as the 77, the 777 was rolling out, and they say, well, where's our next opportunity? And so they started looking at really three different areas. And you can see on this graph, this is plotting the range and the number of seats. And those are really the two most critical parameters for a commercial airliner. Is how many passengers can we put on board this aircraft and how far can it fly? Because the airliners will be looking at that, to basically fill their market. So where can this aircraft travel to? Point A to point B. How many people can we put on it? how many tickets can we sell. And so if you look at this, you can start to see the gaps in this plot. And so there were three areas that Boeing was looking at. One of these was this gap way up here, super wide body jets, right? So something larger than the 747. And so that's where the Boeing, as they called it, the NLA, was their next generation large aircraft. So something that would supplant the 747. The thing about this is it's a relatively small market. You can only sell so many of these. So these are typically going to be your long haul aircraft lines, your transcontinental, your transoceanic type of routes. So Boeing decided not to go down that path, and they said, "Well, we'll just extend our 747 offerings," and that's where the A380 came in. And so the A380, a successful aircraft, began a limited market. So on the other side, they're looking at say, well, our most popular aircraft is a 737. So there's some way that we can retrofit that system, and that's where they were looking at the 7J7. We'll come back and talk about that later. Talk about some aircraft concept. Essentially, an enhanced, more efficient version of the 787. Instead, what they decided to do is, well, let's explore this space over here. Something that's going to give us extended range and capability with a moderate passenger payload capability that would fill this particular niche. So still a long haul aircraft, but customers would be able to buy more of them rather than less. And that would force them to focus on taking this same type of aircraft technology in the 767 and the 777 and improving it with aircraft advancements. What can we do to make this aircraft more efficient, which will allow us to fly farther? So that's the direction that they took. And part of this was looking at their market. Say, well, if we look at the history of the number of aircraft and the number of passengers over a year, those two things may not always necessarily track with one another. And what you can see here is as passenger growth increased in time through the 60s and the early 70s, the number of aircraft also increased. And then the wide-body transports were put into service. And that actually reduced the total number of aircraft that were in service. Because now instead of having 2 or 3 aircraft to take the number of passengers on these long-haul routes, you would be able to do this in one a jumbo aircraft. But the passenger count still grew, and so that's where you see the development of aircraft like the 767 and the 7777 being able to fill this gap. And again, we expect this number of passengers to grow, so you have to be able to look at your market and use this in tandem with your engineering to figure out where those key gaps are going to be at. Now this leads us to some basic back of the envelope type of engineering. Why is there going to be this upper limit, for example, in terms of aircraft size? And part of this, again, we can just use basic physics. So go back to that square cube law and what those trends are going to be. So, if we say, well, how many people can we actually fit in an aircraft? We essentially have a cylinder. That cylinder is going to relate directly to the size of the wingspan on the aircraft. And now we have to start thinking about this from a logistical standpoint. Why, don't we want to build an 1,000 passenger aircraft, for example? So in this case, when you start looking at the size, there has to be an upper limit because you can't always fit this aircraft into an airport. There's not going to be a gate that's going to be able to fit this larger size. Another aspect of it is the actual direct operating costs that you'll have with the aircraft. So how many dollars does it cost per seat per mile that the aircraft is actually traveling? And you start to decrease that as you make the aircraft bigger. It's the economy of scale. But at some point, when you have these larger aircraft, they also become harder to maintain and harder to service. So you start losing some of that benefit. Okay, so you come back and look at the knee and the curve here, and you find, well, this is really kind of my optimum point that I have. And so that's why Airbus, has that kind of magic number of around 600 in terms of their overall passengers. So again, you can pull this out by looking at the overall data and then doing your benchmarking from this directly. So again, if you look at this classic configuration, evolution starting back with, our first, popular conventional jet transport design, the Boeing 707, and we see how that's evolved. That configuration has more or less stayed the same as it grows. You look from the 707 to the 747 to that NLA concept, and then the A380 as part of that. So the trends in the overall aircraft design have stayed the same, even though the scale gets larger and larger. Now, as I mentioned, there are issues with this, right? So even if you can build it, doesn't mean that it's necessarily going to work from an operational standpoint. So let's look at some of the configuration issues with a jumbo jet, for example. So take this giant NLA concept. So you end up with first runway. As your aircraft gets bigger, what else scales with it? Well, it's your takeoff distance. So that means you are only going to be limited to operate from the longest of runways. Then you also have taxiways. So as your aircraft gets bigger, so does the wheelbase on your landing gear. And so you're going to be exceeding the capability, both in terms of the width of the taxiways and the turn radius that you have with the aircraft. So I already mentioned you have terminal gate limits. This maximum wingspan that you have, how many gates across the world can you actually fit this aircraft in? How many have to be modified? Now you also have a lot of FAA regulations that will come into play that dictates things such as, well, you're going to have 90 seconds to get all the passengers off your aircraft in the case of an emergency. You have to be able to demonstrate that. And if if you can't do that, then you have to change your configuration. So, for example, coming back and looking at all these and the Boeing's NLA concept, this double decker, all these emergency evacuation points, and you have to actually go through the process of demonstrating that. So there are a number of other things that come into play. As you get larger, the aircraft get noisier, the wake vortices get stronger, the stresses in your wing skin become an issue, and so that's where you start to look at different engineering in terms of composite materials. So you have to consider all of these things when you look at these new designs and as you go through the scale. So I mentioned that the wake vortex one, this is a combination between physics and FAA regulations. So as we have this aircraft generating lift, our wake vortex gets shed behind it, and that creates a hazard for following aircraft. So the FAA has developed standards for following aircraft for this separation, so you have a wake vortex separation requirement, and it's based upon the size of the leading aircraft and the following aircraft. So the largest separation gap is 10 nautical miles. So, if you think about that overall range, what that now does is it limits your takeoff and landing capabilities or your windows that you have at airports. So again, that becomes a restriction in terms of the amount of traffic that you can put into an airport. And there's even, from a physics standpoint, this regulation is, more or less empirical, is kind of what we think it should be. There's nothing magical about that 10 nautical mile number or any others numbers, for example, that just seems safe enough. It may not even be safe enough. And you can see the persistence of these vortices by the aircraft shown here, actually using a natural, an urban fire as ad hoc flow visualization. So again, this takes us back to benchmarking, right? So what can you do? We've already talked about this one in the past. When you look at the number of passengers and the overall range, you plot that and you say, well, as my aircraft gets larger, I tend to see that it gets farther, right? Well, that again makes sense from an engineering operations standpoint. As my aircraft gets larger, I'm not going to use it for these smaller segments. I'm only going to use it for cross-continental or transcontinental type of flights. But we can generate trend lines that allow us to plot this and say, well, now if I want to develop a 600, 700, 800 passenger aircraft, I can use these curves to make a prediction about what may happen in terms of the range. Doesn't mean it's going to make sense physically, or even since from an operations standpoint. You can use that to make that prediction. More importantly, rather than extrapolation, is the interpolation, right? You can come in and say, well, I'm developing a 250 passenger aircraft. This gives you a sense of where that market may be. Doesn't mean that those other market segments may not be possible, but it does allow you to predict what the minimum capabilities are probably going to be driven by. And so you see a lot of scatter in that plot. Again, that's based upon the fact that you have a lot of these operating requirements coming in and being driven by various use cases by the customer. Now, something more direct physics is taking the number of passengers with the overall takeoff weight. Passengers are payload, so as we scale the payload up, we expect the takeoff weight of the aircraft to scale as well. So this is a very direct correlation, and so this then becomes a really firm way to go through the process of predicting and say, oh, okay, I'm going to develop a 500 passenger aircraft. I can look at this plot and say, well, I should be somewhere within this range with error based upon what other aircraft look like that have been developed in the past. And if you exceed this, that means you're going to be too inefficient. And if you get below that, that means, hey, great, you found some new physics that's actually going to make your aircraft more acceptable, or your numbers are just complete crap, and so you shouldn't believe them. And so, again, these become very useful comparison tools that you can use for that overall design process. Now, as I mentioned, you look at the Boeing's concepts and where they need to fit, these new aircraft designs. And so what they were looking at, when they had the current 747 offering as well, should we develop this, NLA concept, or can we take our current set of aircraft that we have, the 747, and then extend them? So that way, from a aircraft or product standpoint, you don't have to develop an entirely new aircraft. You still have to go through a lot of engineering and a lot of certification, but this gives you a lot more flexibility. And that was Boeing's path to really kind of compete in both of those markets, rather than saying, well, we can't build both the 787 and an A380 like aircraft or Boeing's NLA, but we can extend our capability with the 747 and try to undercut that market, since this aircraft may be competitively priced at a cheaper overall cost than something like an A380. Now, as part of this benchmarking is looking at the market survey, right, where you go out and you look at existing aircraft which are going to closely satisfy the mission requirements that you have. So what you need to do is look at similar types of missions, because they don't have to be exact. Think about this from a payload capability, a physics standpoint, the type of environment that's going to be flying in, and then start to differentiate how your aircraft needs to be different based upon the overall requirements. And then you can use this benchmarking, right, to start to try to drive some of these comparisons. Now, there are lots of sources for this. Jane's All the World Aircraft is an excellent resource to go to. Aviation Week is another one, but obviously, getting the data directly from the internet is also possible, and so you just have to, figure out where you can get that data actually from. Now, once you have this, you can really start to focus on some of these aerodynamic benchmarking. Now, this data is typically harder to come by, and so that's where it becomes a little bit tricky. But this will help you, again, drive what your requirements need to be for your aircraft if it's going to be competitive. Now, just a couple of examples here. Prevent some results by Babakian, which is a great resource to look at, and is primarily looking at the development of these systems for a next generation transport category aircraft, but look at the evolution of these systems over time. Now, what I like about this is it does make sure that you differentiate the different types of aircraft. So, that way we have to take into account that not all things are equal. So we have to be careful, when we're comparing apples to oranges so that we don't make wrong conclusions based upon our particular aircraft design. So trends of L over D, for example, your measure of your aerodynamic efficiency that you have on your aircraft, show that it's relatively flat, right? There's not a huge amount of improvements over time. There's only so much you can do with the aerodynamic physics, but it does tell us where we need to be. And specifically what you can look at is like something on the Boeing aircraft and pick out things like the 767, next generation 747, and the 777, say, oh yeah, we have slight improvements over this. And then you come back and compare that with the 737 and say, well, it's a different category of aircraft. It's meant to be operated a little, less expensively than the other aircraft. So these lead you into drivers then for your particular aircraft design. Where's that efficiency come from? Now we'll start to pull this out when we talk about three-dimensional wings. So when we take our 2D airflow profiles and turn that into an actual wing with a finite span, we find that there's a direct correlation between the maximum lift-to-drag ratio that we have and our overall wingspan or aspect ratio of the aircraft. And again, if we want to try to make that improvement, we can go back to these basic physics. And this is an excellent plot to start to look at, which compares basic geometry characteristics of your aircraft with the maximum lift-to-drag ratio that is possible from that. And so you can start to derive this then with your aircraft design, thinking about this from the limitations of your operational requirements. Obviously, you'd like to have as high a lift-to-drag ratio as possible, but for a commercial air transport, there's going to be a practical limit. You can exceed that on other types of aircraft design, such as a glider, which does not have those same type of operating constraints. It's a little bit smaller, it's not going to have the same type of wingspan constraints that you would have with the commercial airliner. So it's very difficult to make an air transport aircraft look like a glider and get these really high lift-to-drag ratios. Structural benchmarking is one that we've talked about quite a bit. This is a slightly different comparison. This is looking at the operating empty weight, which is essentially you have everything on the aircraft but the payload and the fuel. So you're ready to gas it up, put your payload on, and take off. Again, what we have, is a slight uptick in this ratio over time, but relatively flat. Again, there's only so much that we can do with the structure. We'll come back and talk about this with some of their newer aircraft design. Let's go and look at another one which we do see a lot of improvement in, which is the thrust-specific fuel consumption. Now, again, you have to take into account the different type of aircraft. Go back to the previous plot. What you will notice is there is delineation, differences between large aircraft, regional jets, and turboprops, right? So you have these smaller aircraft end up paying a larger penalty as you get higher and higher. So turboprops don't tend to be as efficient from an a structural standpoint as larger aircraft tend to do. You also see these delineation in the fuel consumption benchmarking, where the types of aircraft are broken down by the types of propulsion systems. I mean, those two things are directly linked with one another. So again, we have our turboprops, our regional jets, and our large jets. Now, what you'll notice in this is, wow, your regional jets are quite a bit more inefficient. They're using more fuel per pound of thrust that they're generating than the larger jets do, but the turboprops actually blow them out of the water, right? So you end up having a much better fuel efficiency down here than you do up here. So that's one a trend that you notice. And so one of the questions you have to ask yourself is, well, if I'm developing a new aircraft, maybe it's more efficient to use something like this rather than something like this. But you have to take into account your market. Your customers tend to want a jet aircraft rather than turboprop driven aircraft, even if a turboprop may be more efficient. Other aspect of this is that you have this trend decreasing over time. Right? So now if you're going to be developing an aircraft out here somewhere, you should be able to reasonably expect that your thrust-specific fuel consumption is going to improve for these future offerings as well. So finally, as part of this, you also want to make sure you consider the regulatory aspect of your design. Let's put this in terms of the design requirements. you're going to have to meet some additional requirements as part of your overall design. If you have an air transport aircraft, for example, then in this case it specifically means that you have to meet all these regulatory requirements. If you have something else that maybe operating in commercial airspace, yeah, you'll still have to meet those requirements. They just may not be as stringent as something that you would have for an air transport requirements. But you still have to go through and check all those boxes. If you're designing something, for a military operation or scientific mission that may not be operating in the national airspace, such as an aircraft for NASA, you're still going to have design requirement drivers that you have to be able to satisfy to demonstrate that your aircraft is going to be airworthy. So it's not enough just to say, yeah, this aircraft design is fine. You have to be able to demonstrate that through a very rigorous engineering analysis.